Hello everyone, tonight we're diving into one of the most mind-bending discoveries in modern cosmology. Picture this, 13.8 billion years ago, in a space smaller than a grain of sand, the entire universe explodes into existence. You've probably heard it called the Big Bang, and like most people, you've probably imagined it as a silent explosion in the vacuum of space. But here's the thing that'll keep you awake tonight. The Big Bang wasn't silent at all. In fact, it screamed. So, if you enjoy exploring mysteries and the unknown, please take a moment to like and subscribe, but only if you truly enjoy what I am saying here. And let me know where you are tuning in and what time you are tuning in the comments. It's always fascinating to see people from all over the world joining us. Now, before you start wondering if sound can travel through the vacuum of space, spoiler alert, it can't. Let's talk about what the universe looked like in those first few moments. The universe wasn't empty space back then. It was a seething, roiling ocean of subatomic particles, energy, and pure chaos. Imagine the most crowded subway car you've ever been in. Then multiply that density by about 10 to the power of 94. That's how tightly packed everything was in the first fraction of a second after the Big Bang. The temperature was around 10 billion degrees Kelvin, which is roughly 600 million times hotter than the core of our Sun. At these ridiculous temperatures and densities, matter couldn't form atoms as we know them. Instead, the universe was filled with what physicists call a plasma, made soup of protons, neutrons, electrons, and photons, all bouncing around like caffeinated pinballs in a cosmic arcade machine. And here is where things get interesting. This plasma could carry sound. At its most basic level is just pressure waves, moving through a medium. You clap your hands. You compress the air molecules in front of your palms. Those molecules bump into the ones next to them and so on until the wave reaches your ears. No air, no sound. T is why space movies get it wrong when they show explosions with dramatic sound effects. But the early universe wasn't empty space. It was the densest, most conductive medium that has ever existed. Every quantum fluctuation, every tiny irregularity in density created pressure waves that rippled through this cosmic plasma, like thunder rolling across the sky. The mainstream scientific consensus holds that these acoustic oscillations large-scale structure. Without these sound waves, we wouldn't have galaxies, stars, or planets. We certainly wouldn't have life. The universe would have remained a smooth, boring expanse of evenly distributed matter, with no interesting features whatsoever. But here is a quirky detail that most textbooks don't mention. The frequency of these primordial sound waves was incredibly low. We're talking about wavelengths that spanned millions of light years. If you could somehow have been floating in that early universe with a pair of cosmic headphones, you wouldn't have heard a scream or a roar. You would have heard something more like the deepest, most resonant bass note imaginable. So low that it would have taken hundreds of thousands of years for a single wave to complete one cycle. Some researchers have speculated, and this is where we venture into academically debated territory, that these acoustic waves might have had a harmonic structure, like a cosmic chord played on the universe's largest organ. The idea suggests that the Big Bang didn't just produce one fundamental frequency, but a complex symphony of overlapping waves at different scales. If this is true, then the universe's first sound wasn't a simple scream. It was more like a cosmic orchestra tuning up, with each instrument representing different physical processes in the early universe. Of course, here is a catch to all of this cosmic music. You couldn't actually hear it, even if you had been there. Not because it was too quiet, but because your ears, assuming you somehow had ears in a universe where atoms couldn't form yet, wouldn't have been able to process frequencies that low. It's like trying to hear the sound of a continental drift or the rotation of the Earth. The waves were there, they were real, and they were shaping the universe, but they were operating on temporal and spatial scales that make human perception look like a fruit fly trying to understand the glacier. The energy driving these acoustic oscillations came from the cosmic equivalent of a battle royale between matter and radiation in those early moments. Photons, particles of light, carried so much energy that they could create matter and antimatter pairs just by colliding with each other. Meanwhile, the matter was so dense that it kept absorbing and re-emitting photons, creating a constant tug-of-war between gravitational forces, trying to collapse things inward. When radiation probing, this cosmic wrestling match created the pressure variations that drove those primordial sound waves. Every tiny region of space was expanding and contracting like a speaker cone, generating acoustic waves that propagated through the plasma at about 1/3 the speed of light. And here is the beautiful part. Those waves are still with us today. They've been stretched and cooled by the expansion of the universe, but they're still there, encoded in the cosmic microwave background radiation that fills every cubic centimeter of space. We're literally surrounded by the fossilized echoes of the universe's first scream, transformed into a gentle whisper that we can detect with sensitive radio telescopes. The cosmic plasma that filled the early universe wasn't just sitting there making noise for the fun of it. It was conducting what might be the most complex symphony ever performed, with pressure waves dancing through the medium at precisely 57,000 kilometers per second. That's about 1/6 the speed of light, which sounds fast until you realize that in the early universe, even slow was ridiculously fast by any reasonable standard. These acoustic oscillations had a rhythm all their own. The fundamental frequency of the universe's first sound waves corresponded to regions of space that were just the right size to complete exactly one oscillation cycle during the first 380,000 years after the Big Bang. Imagine a cosmic drum that takes nearly 400 millennia to complete a single beat. That's the kind of patience the universe had back then. Unlike my neighbor's dog that can't go 5 minutes without barking at absolutely nothing, the mainstream scientific understanding tells us that these oscillations created what cosmologists call baryon acoustic oscillations, or BAOs. Think of them as the universe's way of setting up a cosmic grid system. Regions where the pressure waves reached maximum compression became the seeds for future galaxy clusters, while the regions of minimum compression became the cosmic voids we observe today. It's like the universe was playing a massive game of three-dimensional chess, except instead of pieces, it was moving around entire future galaxies. But here is where things get deliciously weird. Some researchers have calculated that if you could somehow record the sound of these early universe oscillations and speed them up by a factor of about 10 to the power of 26, they might actually sound musical to human ears. The harmonic ratios between different frequency components supposedly follow patterns similar to those found in naturally occurring musical scales. Of course, speeding up cosmic events by that factor is like trying to watch a mountain grow in real time by fast-forwarding 1 billion years of geological footage. The plasma itself was behaving like the world's most exotic musical instrument, and like the air in Earth's atmosphere, which is mostly empty space, with the occasional molecule wandering around. This cosmic medium was so dense that every particle was constantly bumping into its neighbors. The electrons couldn't settle down into nice, stable orbits around atomic nuclei because the ambient temperature was hot enough to instantly strip them away again. So you had this roiling sea of charged particles, all electrically interacting with each other, creating a medium that could conduct both sound waves and electromagnetic radiation. The pressure waves moving through this plasma weren't just simple compressions and rarefactions like you'd find in air. They were coupled with electromagnetic oscillations, temperature fluctuations, and gravitational effects, all working together in a cosmic feedback loop. When a region of plasma got compressed by an acoustic wave, it heated up, which increased the radiation pressure, which pushed back against the compression, which created new waves propagating in all directions. Meanwhile, the slightly denser regions were also gravitationally attracting more matter, which created additional compression, which generated more heat, which produced more radiation pressure. It was like watching a cosmic engine that ran on its own contradictions. Some of the more speculative theories, and this ventures into academically debated territory, suggest that these acoustic oscillations might have influenced the formation of primordial black holes. The idea is that in regions where multiple pressure waves converge, the resulting compression could have been intense enough to create gravitational collapse even before normal matter could cool down and form stars. If this happened, then the universe's first scream might have directly created some of the black holes we observe today. Of course, proving this connection requires mathematical mathematics. Now here is a detail that'll make you appreciate the sheer absurdity of cosmic scales. The wavelength of the fundamental acoustic mode in the early universe was about 2 degrees on the cosmic microwave background. That might not sound impressive until you realize that 2 degrees on the cosmic microwave background corresponds to a distance of about 150 million light years. In today's expanded universe, the universe was essentially humming a tune where each note spanned the distance that would take light 150 million years to cross. It's like listening to a song where each beat lasts longer than the entire history of complex life on Earth. The plasma medium that carried these sounds was also doing something that modern physics still struggles to fully understand. It was creating its own space-time geometry. Einstein's general relativity tells us that matter and energy curve space-time, but in the early universe, the density was so high that these acoustic waves were literally bending reality. As they propagated, regions of high pressure didn't just contain more matter. They actually had slightly different geometric properties than the regions of low pressure sound waves were sculpting the fundamental structure. The coupling between matter and radiation in this cosmic plasma was so tight that photons couldn't travel more than a few centimeters before being absorbed and re-emitted by charged particles. This meant that light itself was trapped in the sound waves, carried along like passengers on a cosmic subway system. Every oscillation in the plasma density created corresponding oscillations in the electromagnetic field, which meant that the universe's first sounds were also its first light show. The acoustic waves were painting patterns of brightness and darkness across the cosmos, creating a visual symphony to accompany the audible one. As the universe continued expanding and cooling, the wavelengths of these acoustic oscillations were getting stretched, along with everything else. What started as relatively high frequency vibrations, Doppler effect, happening in slow motion. The universe was essentially changing its tune as it aged, transitioning from high-pitched cosmic screams to deeper, more resonant tones. 380,000 years after the Big Bang, something remarkable happened that would forever change the nature of sound in the universe. The temperature finally dropped below 3000 Kelvin, still hot enough to melt copper, but cool enough for electrons to start settling into stable orbits around atomic nuclei. This moment, called recombination, marked the end of the cosmic plasma era and the beginning of what astronomers call the Dark Ages. But more importantly for our story, it was the moment when the universe's first scream finally fell silent. The mainstream scientific consensus holds that recombination created what we now observe as the cosmic microwave background radiation, or CMB. Think of it as the universe's baby photo taken at the moment when it became transparent to light for the first time. But here is what makes this discovery so extraordinary. Those temperature fluctuations we measure in the CMB are actually the fossilized imprints of the acoustic waves that had been propagating through the cosmic plasma for nearly 400,000 years. We're literally looking at the visual record of the universe's first sounds. The European Space Agency's Planck satellite, launched in 2009, mapped these temperature variations with unprecedented precision. The resulting image shows tiny hot and cold spots scattered across the cosmic microwave background, each one corresponding to regions where acoustic waves had either compressed or rarefied the primordial plasma. It's like looking at the frozen surface of a pond and being able to reconstruct the pattern of ripples that was spreading across the water just before it turned to ice. Now here is where things get deliciously nerdy. Scientists have actually figured out how to convert these temperature fluctuations back into sound in 2013. Physicist John Kramer at the University of Washington took the power spectrum data from the Planck satellite and used it to reconstruct what the acoustic oscillations would have sounded like if you could speed them up and shift their frequencies into the range of human hearing. The result was a 47-second audio file that represents 100,000 years of cosmic evolution compressed into less than a minute. It sounds like a deep, resonant hum that gradually rises in pitch. It's the universe warming up its cosmic vocal cords. But here is the quirky part that most people don't realize. The sound file you can find online isn't exactly what the early universe sounded like. It's more like a cosmic remix, with the frequencies shifted up by about 50 octaves and the timescale compressed by a factor of about 10 to the power of 15. It's the acoustic equivalent of taking a geological time lapse of mountain formation and speeding it up until you can watch it like a normal movie. The original cosmic sounds were so low in frequency that a single wave cycle took longer than the entire recorded history of human civilization. The temperature fluctuations preserved in the cosmic microwave background reveal a pattern that's both random and structured, chaotic and organized. On large scales, the hot and cold spots appear randomly distributed like static on an old television screen. But when you analyze the statistical properties of this pattern, clear acoustic signatures emerge. There are preferred angular scales where the temperature fluctuations reach maximum amplitude. Exactly what you'd expect if sound waves of specific wavelengths had been propagating through the early universe. These acoustic peaks in the CMB power spectrum are smoking gun evidence that the universe really did have a voice in its early years. Some researchers have pushed this analysis even further into academically debated territory. They've suggested that the harmonic structure of the cosmic microwave background might contain information about exotic physics that operated during the first fraction of a second after the Big Bang. The idea is that different models of cosmic inflation to hypothetical period would have left slightly different harmonic fingerprints in the sound waves. By analyzing the cosmic background radiation with sufficient precision, we might be able to hear echoes of processes that happened when the universe was less than a billionth of a billionth of a billionth of a second. The cosmic microwave background also reveals something fascinating about the geometry of space itself. The angular size of the acoustic peaks tells us that the universe is geometrically flat to within less than 1% in a curved universe. The apparent size of objects at great distances would be distorted, like looking at the world through a funhouse mirror. But the acoustic peaks appear exactly the size they should in a flat universe, which means that sound waves in the early cosmos were propagating through space-time that was remarkably close to Euclidean geometry. The universe's first scream was traveling through the cosmic equivalent of a perfectly tuned concert hall. The precision of these measurements is genuinely staggering. We can determine the temperature of the cosmic microwave background to 6 decimal places, 2.72548 Kelvin, above absolute zero. That's like measuring the temperature of your coffee and being accurate to within a few thousandths of a degree, and buried in those tiny temperature variations, typically just a few hundred millionths of a degree, the entire acoustic history of the early universe. What makes this even more remarkable is that we're detecting these signals from a time when the universe was about 1,000 times smaller than it is today. The acoustic waves we're observing had wavelengths of a few million light-years when they were generated, but cosmic expansion has stretched them to scales of hundreds of millions of light-years. It's like listening to a recording that's being played back at 1,000th of its original speed. The cosmic microwave background is also incredibly uniform. The temperature varies by only about 1 part in 100,000 from place to place. This uniformity is actually a major puzzle in cosmology, because regions of the CMB that are separated by more than a few degrees on the sky should never have been in causal contact with each other. There shouldn't have been enough time for them to reach thermal equilibrium. The fact that they all have nearly the same temperature suggests that something happened in the very early universe to synchronize conditions across vast regions of space. Those acoustic oscillations we've been talking about might be part of the answer to this mystery. Remember that cosmic remix we talked about earlier? Well, it turns out that translating the universe's ancient acoustic signature into something human ears can appreciate is only the beginning of what scientists have discovered lurking in those primordial sound waves. The process of converting cosmic microwave background data into audible frequencies reveals harmonic patterns that would make even Bach jealous of the universe's compositional skills. The Keynesian scientific approach to this acoustic archaeology involves something called spherical harmonic analysis. Imagine taking the cosmic microwave background is essentially a picture painted on the inside of an enormous sphere surrounding Earth and breaking it down into its component wave patterns, like decomposing a complex musical chord into its individual notes. Each harmonic mode corresponds to a compatic. The mathematics involved makes advanced calculus look like finger painting. But the results are surprisingly elegant. When John Kramer created his famous sonification of the cosmic microwave background, he discovered that the universe's first sounds contained at least 6 distinct harmonic modes. These Pexion and rarefaction waves completed exactly 1, 2, 3, 4, 5, or 6 oscillation cycles during the radiation-dominated era. It's like the universe was playing a cosmic major chord, with each harmonic adding richness and complexity to the overall acoustic texture. But here is where things get wonderfully weird. The relative amplitudes of these harmonic peaks encode information about the fundamental composition of the universe. The height of the first acoustic peak tells us about the curvature of space-time. The second peak reveals the ratio of ordinary matter to dark matter. The third peak provides clues about the amount of dark energy driving cosmic acceleration. Each harmonic mode is like a cosmic instrument in an orchestra, and by listening carefully to how loud each instrument plays, we can reconstruct the entire score of cosmic epidemically. Debated Terioff, these would be ripples in space-time itself, generated during the inflationary epoch that preceded the acoustic era. If such gravitational wave signatures exist in the CMB data, they would represent the universe's first percussion section, rhythmic distortions in the fabric of reality that accompanied the melodic acoustic oscillations. The challenge is that these signals would be incredibly faint, buried beneath multiple layers of cosmic noise and interference. Now here is a detail that will make you appreciate the absurd precision of modern cosmology. Scientists can extract meaningful acoustic information from temperature fluctuations that are smaller than the width of a human hair when viewed from the distance of the moon. The Planck satellite measured variations in the cosmic microwave background that correspond to energy differences of about 1 part in 100,000. That's like detecting the difference in brightness between a 100-watt light bulb and a 99.999-watt light bulb from a distance of several miles. And from these microscopic variations, we've reconstructed the acoustic history of the entire observable universe. The frequencies present in Kramer's cosmic sound files span about 2 octaves, ranging from what would be a very deep bass note to something approaching the lower range of a baritone singer. If the universe had continued its acoustic performance and we could still hear it today, it would sound like the world's largest pipe organ, playing a chord that encompasses notes separated by roughly the same interval as the lowest note on a piano and middle C. Of course, by the time recombination occurred, those cosmic sound waves were already shifting toward lower frequencies due to the expansion of the universe. The acoustic oscillations that started as high pre-compression waves in the dense primordial plasma were gradually being stretched and redshifted like the changing pitch of an ambulance siren as it drives away from you. Except in this case, the ambulance was the entire universe, and it was accelerating away from itself in all directions simultaneously. The end of the acoustic era didn't happen all at once. Recombination was a gradual process that took about 100,000 years to complete. During this transition period, the cosmic plasma slowly became transparent as more and more electrons settled into stable atomic orbit. The acoustic waves continued propagating, but they were gradually losing their medium. It was like watching a symphony orchestra where the musicians were disappearing one by one, until eventually only the echo remained. The last acoustic waves to propagate through the cosmic medium had wavelengths corresponding to the largest structures we observe in today's universe. These final cosmic sound waves left their imprint on the distribution of galaxies and galaxy clusters, creating a pattern that astronomers call the Baryon acoustic oscillation scale. Even today, 14 billion years later, we can measure this characteristic length scale in large-scale surveys of galaxy positions. It's about 450 million light-years. What makes this discovery particularly remarkable is that it provides an independent confirmation of our understanding of cosmic evolution. The acoustic signatures preserved in the cosmic microwave background tell the same story as the large-scale distribution of galaxies, the observed abundance of light elements, and the expansion multiple witnesses. It's like having multiple witnesses to a cosmic crime scene, and they're all giving consistent testimony. The transition from sound to silence also marked the beginning of what cosmologists call the Dark Ages, a period lasting several 100 million years, when the universe contained no stars, no galaxies, and no sources of light other than the gradually cooling cosmic microwave. The moment when the universe finally stopped screaming wasn't dramatic, like a crescendo ending with a cymbal crash. It was more like a cosmic fade-out, with the acoustic oscillations gradually losing their grip on reality as the medium that carried them simply ceased to exist. As recombination progressed, and neutral atoms formed the tight coupling between matter and radiation that had enabled sound waves to propagate through the cosmic plasma. Photons, which had been trapped in an endless cycle of absorption and re-emission, suddenly found themselves free to travel through space without interference. The universe became transparent for the first time, and with that transparency came the end of its acoustic era. The mainstream scientific understanding tells us that this transition happened when the universe was about 380,000 years old and had cooled to roughly 3000 Kelvin, but the end wasn't instantaneous. It was more like watching a thick fog gradually lift on a summer morning. Different regions of space became transparent at slightly different times, creating a complex pattern of acoustic cutoffs that astronomers can still detect in the fine structure of the cosmic microwave. The last sound waves to propagate through the cosmic medium were stretched by expansion until their wavelengths reached truly cosmic proportion. These final acoustic modes had periods measured in millions of years and wavelengths spanning hundreds of millions of light years. They were like the universe's final, impossibly low bass notes, played on an instrument the size of galactic superclusters. And then, quite suddenly, in cosmic terms, the music stopped. Here is where the story takes on an almost melancholic quality. Those acoustic oscillations didn't just disappear when recombination ended. They transformed into something else entirely. Gravitational waves rippling through the newly transparent universe at the speed of light. Some researchers have ventured into academically debated territory by suggesting that these primordial gravitational waves might still be detectable today, including the polarization patterns of the cosmic microwave background. If this is true, then the universe's first scream didn't really end, just changed from audible sound to gravitational music that we're only now learning how to hear. The silence that followed recombination lasted for several 100 million years, a period cosmologists call the Dark Ages, with good reason. No stars had formed yet, no galaxies existed, and the only light in the universe came from the gradually cooling amphon. During this era, the universe was filled with vast clouds of neutral hydrogen and helium, slowly collapsing under their own gravity to form the first generation of stars. But these gravitational collapses happened in profound cosmic silence. There was no medium dense enough to carry sound waves across the emptiness of space. It's a haunting thought that for hundreds of millions of years the universe was completely quiet for the first time since its birth. Now here is a quirky detail that most cosmology textbooks don't mention. If you could somehow have been floating in space during the Dark Ages with a sensitive radio receiver, you might have been able to detect the 21-centimeter radiation emitted by neutral hydrogen atoms. This faint signal, generated when hydrogen electrons flipped their spin states, would have been the universe's only voice during its silent period. But calling it a voice is generous. Would have been more like the universe whispering to itself in the cosmic equivalent of a library where even breathing feels too loud. The end of cosmic silence came with the formation of the first stars roughly 200 million years after recombination. These primordial stellar furnaces began the process of reionization, gradually heating and ionizing the neutral hydrogen. But this new era of cosmic activity didn't restore the universe's ability to carry sound. Sin remained a vacuum, and while explosions and stellar processes could generate shock waves and electromagnetic radiation, the kind of universe-spanning acoustic oscillations that characterized the first 380,000 years would never return. The universe had traded its voice for its vision, the ability to see across vast distances through trench space. When we look at the cosmic microwave background today, we're seeing the fossilized image of the universe at the moment when it stopped screaming and started blowing. Those tiny temperature fluctuations, preserved like ancient footprints in cosmic amber, are all that remains of the most magnificent acoustic performance in the history of the universe. The patterns we observe interpose not just the physics of sound propagation through primordial plasma, but the entire history of cosmic evolution from the first fraction of a second after the Big Bang through the moment when matter and radiation finally parted. Waves every message into an echo of the cosmic microwave background is like lead shifted and transformed, but still carrying the harmonic signature of the universe's first song. And perhaps most remarkably, we've learned that the universe's acoustic phase was absolutely essential for creating the conditions that would eventually allow life to emerge. Without those primordial sound waves, matter would have remained smoothly distributed throughout space. There would have been no density fluctuations to seed galaxy formation, no gravitational collapse to ignite the first stars, no nuclear fusion to create the heavy elements necessary for planets and biology. The universe's first scream wasn't just a cosmic curiosity. T was the performance that made everything else possible, including the consciousness that allows us to listen to its echoes 14 billion years later. So, here we are, floating through a universe that once screamed with the voice of creation itself, now listening to its whispered memories in the gentle hum of cosmic background. The silence that surrounds us isn't really silence at all. The transformed echo of that primordial performance stretched by time and space until it becomes the barely audible soundtrack to our existence. Every time you tune a radio between stations and hear that soft static, you are actually listening to the afterglow of the universe's first song mixed with the thermal radiation from countless stars and galaxies. The cosmos hasn't really gone quiet. It's just changed its voice from the thunderous bass of compressed plasma to the gentle soprano of electromagnetic radiation painting patterns across the cosmic microwave background. Tonight, as you drift towards sleep, remember that you are surrounded by the fossilized echoes of that ancient acoustic symphony. The universe sang itself into existence, screamed its way through its first few 100,000 years, and then settled into the quiet contemplation that allows stars to shine and planets to form and life to emerge and consciousness to develop and wander about its own origins. We are, in a very real sense, the universe's way of listening to its own distant memories, transforming cosmic background radiation into the thoughts and dreams that let us recount the story of ever-recent dreams that let us into memories. The first scream lasted 380,000 years. The silence that followed has lasted 14 billion years and counting. But in that silence, the universe learned to dream. And sometimes, if you listen carefully enough, you can still hear the echoes of its first song.